Good morning. How you guys all doing today? So we are gonna continue on with the next concept. This is one I wish I had you guys in school for. Something called the dilation. I have some really cool activities for this. It just doesn't work in distance learning, and it also just won't be able to. We won't have enough time to really delve into all the cool stuff that we can do with it. But it is what it is. So when we hear the word dilation, the first thing that you probably think of, most of you are like, dilation. Think about your eye. Okay, if your eye gets dilated, it means that now we usually refer to it as it gets bigger. The pupil gets bigger. A dilation in math is actually twofold. It's where an object can get bigger or it can get smaller. So now let's look at this picture for a second. Now you guys have done dilations in the past. Oops, that's not the screen I want to be on. This is the one I want to be on. Okay. When you take an image and you use one of the corners, okay, you can make it smaller or you can make it bigger. But as I'm doing this, you notice it's growing lengthwise and height-wise, what's called proportionally. If I use this one, it doesn't look the same, does it? If I do this one, it doesn't quite look the same. If I use any of the corners, I'm going to get an image that looks identical. Okay, everything is in the same proportion. The only difference is the size is different. So it's either bigger or it's smaller. Okay. So you've been doing this for a while. Now we're going to use called a dilation. So what is a dilation? In mathematics, it's basically where we make an object bigger or smaller, but we keep all the proportions the same. Now, this book talks about something called the center of dilation. I'll mention it. We'll talk about it a little bit. It's not overly important for you to fully understand that concept to go into next year. Actually, Mr. Litvack might talk a little bit more about that. So if you look at these two, these are dilated. So you could either say that the blue one is an enlargement of the red one, or you can say the red one is a reduction of the blue one. Doesn't matter to a certain extent. It all matters on where you start from. Okay, and we'll talk a little bit more about that. But if you look at these objects, if you notice what we call corresponding angles, which are angles that are in the same spot. So this angle and this angle are congruent. This angle and this angle, if you look at them, they're congruent. That angle and that angle are congruent. That angle and that angle are congruent. Okay? So in a dilation, corresponding angles always remain congruent. The actual sides, there's they stay at a proportion, the same proportion. But we're not getting into that part of it today as much. So again, is this a dilation? So is the red one a dilation of the blue one, or is the blue one a dilation of the red one? Doesn't matter because you can always go two directions with a dilation. And the answer is yes, it is, because here's where we're talking about the center of dilation. If you were to draw a line through all the corresponding angles, they will reach a point known as the center of dilation. Not overly worried about that, but if you notice, they each will go through and meet at that point. Are either of these a dilation of the other? The answer is absolutely not, because they're the exact same size. Okay, it's not an enlargement, nor is it a reduction. And if I were to draw lines through each of these points, it's not going to come to a certain spot, same spot. So that leads us to the next concept known as scale factor. So a scale factor talks about how much bigger or smaller the new size is. So we're going to start from the red triangle and we're going to go to the blue triangle. So we have A, B, and C. Now this is called a prime, A prime, B prime, and C prime. And the reason why we call it that is because this point relates to point A. This point relates to point B. That point relates to point C, but they're not the same points. All right, this is the points for this triangle. These are the points for that triangle. So if you notice, and I'm just going to tell you these are similar. I'm sorry, they are dilation. If you look at this length, this is a length of 2. This one is a length of 6. This is a length of 2. This is a length of 6. So this line is 3 times bigger than that line. This line is 3 times bigger than that line. Now, if you know the Pythagorean theorem, it'll work here. That's not something I'm going to teach you. If we were in school all year and we weren't doing this distance learning thing, we would have had enough time, and I was going to do that with you. I planned on it, but obviously we can't this year. That's okay. But anyway, you would find that this line is 3 times bigger than that line. So that has what's called a scale factor of 3. It's the number you multiply the side lengths by to get the other side lengths. Okay. So again, here are the points. So we have 0, 2, 2, 0, 2, 2. If you notice, each corresponding point is 3 times bigger. So 0 times 3 is 0, 2 times 3 is 6, 2 times 3 is 6, 0 times 3 is 0. 2 times 3 is 6, 2 times 3 is 6. Okay. So that leads us to what does scale factor look like. Basically, when we have ordered pairs, we don't always have to have ordered pairs. This time we do have ordered pairs. If I just do a regular triangle, there's other ways we could figure it out as well. So from x and y, if it is a true scale factor, x and y are both multiplied by the same number. When they're multiplied by the same number, okay, they're just going to be proportionally bigger or proportionally smaller. How do you know if it gets bigger or smaller? Well, if k is bigger than 1, it gets bigger. Think about it in multiplication terms. You multiply by 1, you get the same thing. Anytime you multiply by a number larger than 1, it will always get larger. Okay. If k is between 0 and 1, it's going to get smaller. It's going to be what's called a reduction. So think about it, right? If you multiply something by a half, it gets smaller. If you multiply something by a third, it gets smaller. If you multiply something by 5/6, it still gets smaller. That's why it's a reduction. So if this is the original, if you're multiplying it by something larger than 1, it becomes an enlargement. If you're multiplying it by something between 0 and 1, it becomes a reduction, like this one down here. So now let's look at some examples. So the vertices of a triangle are this point A, 1, 3, B is 2, 3, C is 2, 1. Draw the image after dilation with a scale factor of 3. Okay, so it tells us the scale factor, which in this case is the variable k. So xy has to equal kx times ky. So since the scale factor is 3, I just put 3 in front of, or shall I say multiply each x variable, each x coordinate by 3, and each y coordinate by 3. So the first one is 0.13. So a prime is going to be 3 times 1, and then 3 times 3. So that comes out to be 3, 9. Point B is at 2, 3. So b prime is going to be 3 times 2 and 3 times 3, which comes out to be 0.69. And then point C is 3 times 2 and then 3 times 1. So C prime is going to be 6, 3. So if I were to put that onto a picture, here's your first one. Obviously, it would be 3, 1. I'm sorry. Whoop, wrong one. 1, 3, 2, 3, and 2, 1. And then you plop your prime points in here. Yes, when you do your work, there's going to be some where you have to plop the points. Not too overly complicated. So now this one's a little different because, oh my gosh, there's negatives. Wait a minute, there's 4 of them. Holy cow, my scale factor's less than 1. Okay, not that big of a deal. So again, so you're going to multiply every x coordinate by 0.5 and every y coordinate by 0.5. I'm not going to go through each and every point here. I think you can figure out 0.5 times negative a fourth. I'm sorry, negative 4 is going to be negative 2. 0.5 times negative 6 is negative 3. Okay, not going to go too much into that, but if you plot the points, now it's going to be a grid that is in 4 quadrants. Okay, so which one is which? So the red one is the original, and then the blue one is the image. Okay, the image with the dilation. So now we talked a little bit about scale factor. If you notice, we went from this one to this one. The scale factor was 0.5. There's actually another scale factor if I went from the small one to the big one. Let's see. 1, 2. 1, 2, 3, 4. 1, 2, 3, 3.5. 1, 2, 3, 4, 5, 6, 7. That's very interesting. Do you notice that this side is twice of that, that side is twice of that? But when we did it, this is half of that. So let's think about that for a second. Half, 2, they are, yes, reciprocals. Let's go back and do this one real quick. Okay? We said, so this is 1, this is 3. This is 2, this is 6. So we used a scale factor of 3. We multiplied this by 3 to get that. This by 3 to get that. Well, what happens? What do I multiply this by to get that? 1/3. So there's always going to be two scale factors that are involved. If it's an enlarged, to make it larger, it's always going to be bigger than 1. If it's a reduction, it's going to be smaller than 1. And the two of them are always reciprocals of one another. Neat little trick. A wildlife refuge is mapped on a coordinate plane where each grid line represents 1 mile. The refuge has vertices 0, 0, 1, 3, and 4, 0. An expansion of the refuge can be represented by a dilation with a scale factor of 1.5. How much does the area of the wildlife refuge increase? Okay, scale factor 1.5. That means I multiply every x coordinate by 1.5, every y coordinate by 1.5. Plug those in, bam, plug those in, bam, plug those in, bam. Now we graph them. So this is something called a nested triangle. We're not going to deal with those right now. But what it's asking you for is how much does the area increase? So we just have to find the area. So we have this triangle here. Now this looks like a J prime. There's also the letter J here. It's a shared point. So JKL has a length of 4 and a height of 3. So 1/2 base times height, that comes out to be 6. I know you can't see it because of that. There it is. Now we have J prime, K prime, L prime. So that's a base of 6 and a height of 4.5. So that is a an area of 13.5. So all we have to do is subtract 13.5 minus 6, and we get a difference of 7.5 miles. 7.5 square miles. So good luck today. Reach out if you have any questions. If not, have a good day. Bye.